Good morning. My name is Mike D. Lecluse, President of Lesman Instrument Company. I'm showing 9 o'clock, so we're going to go ahead and get started. I'd like to thank all of you for taking time out of your busy schedule to join us for Hygienic Level Management Basics for Liquids and Solids. Today we're going to focus on non-contact through air level measurement, and it will be presented by Siemens' Tim Bulbuk. Tim is an application engineer and product promoter for Siemens level and weighing products for the Western United States. He brings more than 20 years experience in process instrumentation, working with customers in food and beverage, chemical, power, water, and wastewater industries. Just in case you would like to review the presentation or share it with a coworker, the presentation and slide deck will be published on our website in the next couple of days. The phone lines are muted. If you have any questions, there's a question tool built in to GoToWebinar. Please just send me the question and I'll get them answered. With that, I'm going to turn it over to Tim.
Thank you, Mike. Good morning, ladies and gentlemen. Appreciate your being here. Like Mike said, I've been involved in the instrumentation. This is actually my 20th year involved in instrumentation, and I worked with quite a few of the different major manufacturers. I had the pleasure of working with some great people over the years, and familiar with some of the earlier technologies that were used. Actually, worked with Corning and some of their acid waste drain systems, and certainly sanitary systems as well. I wanted to get right into this, make this so valuable for your time. The information that we have, feel free to give questions here. We're going to have a lot of information to cover in a short period of time, so if it's something that is application specific, I would say let's hold that toward the end or have an offline conversation. But wanted to, again, appreciate your time, and we'll go through this. Hopefully, and also look forward to getting some feedback from you folks to Mike, and we'll always try to make this better and more valuable. Appreciate it. Let's just start off with a safety minute. Basically, how not to make a snow angel. Notice he has his helmet on. Had the best laid plans of mice and men. Had a plan. Went off plan here. So, okay, hygienic radar. Today we'll talk about what's been done historically. A little bit on terminology, so we can have a little bit later discussions. How important that is when it comes to commissioning and setting up the device. What's new with hygienic measurement. Then I think some valuable information. What's under the hood, what will make it work, what makes it valuable, what makes it unique. Then we'll go into some design and install considerations and a little bit of application by industry. Real quick here, for those who are fairly new to instrumentation, basically you'll hear some terms here from discrete and analog measurements. Basically, a discrete measurement is a simple on or off measurement. We might see along this line here, which we do supply, but a lot more commonly that is used as an alarm, either a high alarm or a low alarm, or an input to a PLC to either turn something on or turn something off. If we have a number of discretes, we tend to get close and closer to a continuous measurement, and that's where analog devices come in, where we're actually measuring and getting to know what the level or process is doing at any given point in time. So these discrete and analog measurements could be temperature, they could be a flow, simple flow rate, but solid engineering practices that generally include that we combine both analog inputs and discrete inputs. So for the applications that we'll be looking at, quite often we use a continuous measurement in an analog mode along with a discrete point measurement. More and more continuous level measurements are preferred. A lot more in the past, where a lot of control was done in the instrumentation. More and more things are being done where we're just providing information to a PLC or the control system to supply information and make sure that that's good and valuable information. If I can have an application, but we want to make sure that what we're supplying is good, valid information to the control room. When it comes to operation modes, the main thing we're going to look at here are the top three. Level, which is simply our 0 calibration point up to a given material surface. We call that level, and we actually, all of the devices that use time of flight to get that measurement indirectly. We do space measurement, which would be from the material surface to some given point above the material surface. And then lastly, a distance measurement, which is actually our transducer face, our flange face, to the material process. This is important because when we have conversations, quite often what we're looking at is setting up for a level application, but we're actually doing a commissioning and setting up. We go into distance mode so we can confirm our measurements. When it comes to using alternate technologies like ultrasonics, we get into flow, differential, and volume calculations as well. Quickly here, the level time of flight principle. We use an echo ranging calculation. If we know how fast we're going and we know how long we've gone, we can develop the distance. When it comes to radar, we're working at the speed of light, which happens to be just under 300 million meters per second. So what we do is actually measure the time of flight, the time between the sound intermission and the echo received at that time, the speed of light times that flight. Now that's going to be the time for the echo, the radar echo, to actually go to the material surface and back. So we basically divide it by 2 to get the actual correct measurement. What we look at is the time of flight times the speed of light, and then we divide it by 2 to get it right. When we look at measurements in vessels, we find that every measurement that we make is actually a differential measurement. So if it's an open vessel, we refer to that as gauge pressure measurement. We're still measuring differential. We just happen to be sharing the same point at the top in terms of an opening in the tank. It's a little more complicated when we're doing closed vessel applications. And some of the challenges there are what helped to develop radar. So quickly here, some of the challenges here would be if I have a process tank that's pressurized and I want to get a proper measurement from a differential pressure device, I have to be able to bring what that pressure is to the device so that I can offset that measurement. Otherwise, if I didn't have this, I would simply see that pressure in the tank as additional product. Okay. So I can do that with either a single transmitter and a wet leg, or I can do 2 separate transmitters, and then I have all the issues of zeroing out the transmitters, taking into account things like the fill fluid, the density of that fill fluid, and height. So zeroing out the transmitter and making adjustments for this becomes important. If I have a process that I need to make sure that doesn't block, I need to put seals on these, so it gets a little bit more complicated. So some of the principles that we're talking here are still making a measurement. Okay. The main thing, again, to get the information is I want to know what's in that tank and the level in that tank. So different technologies have been used in the past to make that measurement. When it comes to radar, what's good about it is it's non-contacting. So I don't have to contact the fluid or the solids that happen to be in the tank. So there are definitely some advantages to that. One is that they're insensitive to vapors and dust. Okay. Also, we can handle fairly high temperatures and pressures, and these are used in solids industries all the way to 328 feet. So very long ranges, very quick response. On the negative side, we have sensitivity to foam. There can be problems with heavy condensate. And when it comes to radar, we don't have the option of going with remote. So it's going to be direct. I can always take that output and go to a separate display, but the general unit itself does not go into a remote remote applications. So when you take a look at all the different applications that are out there and what our choices are when it comes to instrumentation, we can take a look at single pressure applications where we use a single transmitter. This would be for use in an open tank measurement, for example. When we have a vacuum on a tank, I can do the same thing with 2 transmitters, be able to make adjustments for that. When we have solids and dusty applications, different technologies simply work better for those applications. Okay, if I have foam and I'm only trying to measure what's in the process, depending on that foam, that's one of the biggest challenges that we have with all these technologies, because we're talking processes, we're talking something that's dynamic, something that's changing. So that's going to be and quite often is a major topic of conversation. What's the quality of the foam? Is it dry foam? Is it thick? There's a difference between measuring something like a light sudsy soap and something like a beer foam. Okay. The vapors. If we have vapors, it doesn't bother radar, but it causes major problems for ultrasonic, in that when there's vapors in the atmosphere, the speed of sound changes, and that throws off an error. That actually makes the unit, throws it off. If that's consistent and steady, we can make adjustments for it, but it's still a challenge. We can look at low temperature applications, in which case the equipment itself, we look at process connections, we look at materials of construction based on handling very cold processes, or conversely, very hot temperatures. And then we have challenges with agitation. So I can't use a guided wave radar in a tank necessarily where there's an agitator. So I'll be hitting that the sensing rod and causing some problems. So the main point here is we try to let the application choose the technology. So we get specifically to radar, and we talk about early measurement techniques. Quite often what you had was a tank spud that'd be welded to the side of a tank, and then a process diaphragm seal. In this case, we're looking at a tri-clamp style that would fit into that spud, and we would be sealing at the end of the spud. This would actually work well in tanks that had material buildup. You could define the extension length into that process and basically clamp the device here, which works fine, and it's still used a lot today. However, if you have a problem with the device, you can't just remove it. The tank itself has to be completely emptied. Also, there are definitely some challenges in regard to keeping that clean and hygienic, and because we're talking about some crevices in some areas that can cause some problems. In the early days, radar was not suitable for hygienic applications simply because large antennas were required for signal strength because they had very low frequency, and there's a relationship between the frequency and the size of the antenna required. Remember, we're sending out a signal, and we need to be able to get that signal back. So the first ones were more like sonar scopes, or what you see at the side of a football game, in terms of trying to send a signal out and then trying to receive that signal. Okay, so again, radar was not a fit for hygienic applications for years and years. What made the difference was the fact that the experience that Siemens has with ultrasonic equipment, the intelligence that was developed over 30 years has been applied to radar equipment. So when we talk about the process intelligence, the engine under the hood is the same as the sonic intelligence that has been used by ultrasonic equipment. So we're taking the knowledge that we've gained in the ultrasonic and be able to adapt it to the radar. And so process intelligence, we currently have over 1 million devices installed with the echo processing engine in them. We can also adjust the algorithms for liquids. We can adjust for low liquid levels where the radar might pick up the bottom of the tank. We can all do something that we'll call auto fault echo suppression, and this is dynamic. One of the keys with this is that we actually use the strength of the echo signal, and we'll go through that in a moment here, to automatically change and adapt to conditions. So we're not static. We can adjust how we're measuring based on the feedback that we're actually getting. What's nice with this is we actually do this with local programming. So the units themselves can be set for hazardous areas and can be easily programmed based on parameters or the wizards that we talked about briefly. The interface is through the use of a quick start wizard and a handheld programmer. Or via software. And we work with both PDM, AMS, the handhelds. The advantage that you get when you use the software, and it's inexpensive, I think it's under $100, is that you have the visibility to all the parameters simultaneously. You can save parameters, so you can actually go through. Our service guys use this tool quite a bit when they're out in the field because they can actually pull up a device, grab all the parameters, review parameters, save parameters, and do as found, as left records, as well as diagnostics and complete echo profiles. So it's nice to be able to take a look when it comes to setting up an actual tank and or process, and being able to review the application parameter by parameter and make adjustments by those parameters. So also we work with AMS. We can work with the handhelds. However, you don't get the echo capabilities when using the handhelds. So real quick, let's talk about what's under the hood when it comes to anything sonic or process intelligence. The typical obstructions in a tank might be pipes, weld seams, more likely in smaller applications, agitators, internal structures, things that would cause some problems. You can imagine if I have a pipe that's sticking out into the process, I'm going to see that. So what we do is we actually send out a pulse, whether that's radar or ultrasound. We look for that object return signal, and we form an echo profile. We apply some filtering, which we call the dynamic TVT, or time varying threshold, and we take a look at the echoes. Anything above that threshold, we actually analyze. We analyze those with a number of echo algorithms, which are specific to the process and optimized for the process. We then make a selection based on a number of factors in terms of area, largest and first. What echo we use will vary based on the tank itself. We can actually take a look at fault echo suppression, and those things that we see in the tank that we know are going to be there, we put into memory in the unit. So it'll compare all future echo profiles to that original echo. So even though I have that echo up front here, I can actually work around that. perform a learn, and then that auto false echo suppression will no longer see that obstruction. So that's basically the process intelligence under the hood. So some of the key things we take a look at here in terms of design considerations is location. We're working with radar and ultrasonic, both have a beam angle. Over the years, this has been improved. We had to go with very large antennas in the past to try to get a small beam angle. When we take a look at your process, the larger the horn, the smaller the beam angle. The smaller the beam angle, the smaller the footprint. We take a look at a beam angle. We can actually put in, if I know I have a beam angle of 6 degrees, and the height of my tank is 20 feet, I know that my footprint is going to be 2 feet in size. So that gives me some ability to from a design consideration standpoint, okay, I'm not going to put this unit 1 foot from the side of the tank because I know I'll be having some issues with that. So we can take a look at that up front in terms of beam angle and knowing what our footprint size is so that we can adjust accordingly. And that also gives you an example of why you might want to go to a larger process connection, even though you have a space available for a smaller unit, just to get a tighter beam and more accurate measurement with less distraction of what might be obstructions in the tank. And then some of the more common installation criteria would be making sure we're not actually going to see a waterfall or the fill stream when we're actually doing our measurement. When we get into other radar units, we talk about aiming. So the main thing is we're going to be sending out a signal, and we want to optimize the signal that we get back. We're going to take a look at that and actually analyze it. We're going to be able to develop a confidence level in what we see as our material surface to be, and be able to adjust our parameters until we can maximize what that confidence level actually is. When it comes to design considerations, one of the things is real estate in the marshalling panels is quite often at a premium. So, but what you save in material costs or initial costs can be lost down the road in terms of trouble with setting up and communicating with devices. Here we have, actually there were some 24, 26 devices in about a 6-inch area. This is double stacked wiring in a marshalling panel, and spring loaded as opposed to screw connections. So taking about 5 minutes to get a wire out, 5 to 8 minutes to make a connection to be able to talk to a single device. So kind of a bit of a pain in terms of trying to set up and do commissioning. The value of being able to hook up with the software in the marshalling panel is, in this case, on a cold winter day, instead of going to the top of a 50-foot silo or going into a process area that can be hazardous with vapors, whatever, I can actually have connections to the device, the unit's hygienic radar, right from the control room. We can also get set up with HART multiplexers, so that with the software you can actually interrogate and take a look at a device or a number of devices simultaneously. We went into a little bit on this already, but to give you a little better feel for this, today we're talking about more of our hygienic or flange encapsulated antennas. Two things that come into play here. One, based on the antenna size. If you take a look here, in the smaller 2-inch connections size, we're looking at a distance of 33 feet being the maximum available. We get into larger sizes. I have a stronger beam and can measure greater distances. With the LR250, we're looking at 66 feet and 33 feet. And you can see that we get into the larger sizes. We get into smaller beam angles as well. An important note here is the dielectric constant of the material is important in that lower materials, materials with lower dielectric constants, basically don't send as strong a signal back, so they're a little bit harder to measure. But we can measure dielectrics down as long as they're greater than 1.6. So, and most of these dielectric constants have been taken actual physical measurements. A number of the universities in the past actually studied a dielectric constant, so that a reference material is readily available. So the LR250, all this that we've talked about in terms of the intelligence is all in the head. When we talk about the process connections, whether it's a standard flange process connection, a hygienic connection, etc., the main thing to understand here is that the electronics, the brains behind it, have been around since 2007 and are tried and proven. The echo profile is actually visible and can be seen on the device itself. So when it comes to commissioning, the device can be done with a handheld programmer without disturbing our hazardous locations. In other words, no covers have to be removed or whatever to program and to evaluate a device. We can actually zoom in and take a look at the echo profile and do some diagnostics directly at the instrument. So in the past, we had your options were basically going with different materials of construction for process connections, both 316 stainless being the most common, and then a few exotic materials. And now we have PVDF, which is a unit that's a 2-inch unit that is PVDF in the process, 2-inch NPT. And then when we get into the hygienic, we're looking at a high-density Teflon TFM 1600, which was developed by 3M for applications, which allows us to do an extremely dense Teflon that actually has stronger characteristics in terms of less susceptible to permeation and can develop extremely fine finish, an R8 finish. So we have different process connection types. When it comes to the hygienic, now we have, again, the fully encapsulated horn antenna, process temperatures up to 200 degrees centigrade, and then pressures up to 232 pounds. So when it comes to the hygienic itself, we deal in 2-inch through 4-inch in both the aseptic fittings, the 11851 DIN fitting, which is the most common milk coupling fitting, and then the different tri-clamp fittings as well. And then for those of you who get involved in OEM type applications or skids, we do the Tuckenhagen style as well, which you may see more of in the future. That's becoming more common as well. So when it comes to radar, we do offer the widest range of process connections on the market today. Some of the features and benefits we'll get into briefly here. We're looking at a 25 gigahertz pulse radar. A lot of what was on the market earlier was 6 gigahertz. So where there would be a lot of noise, we can get a very strong signal. This is a liquid application. What we see here is a normal echo profile, and then our dynamic TVT. This would be an ideal application for a measurement. When we take a look at it, we can actually see what are not only the the distance in this application, we can actually see where the noise is and evaluate the echo profile and optimize our parameters until we've optimized our profile. So with a 25 gigahertz frequency radar, we no longer have the issues that plague the low frequency unit with noise. Radar by itself, I don't care. You could have a VFD right next to these units, variable frequency drive, a noise bomb, and it's not going to affect radar. We're looking at the frequencies that we're dealing with are not affected by that type of equipment. So we have less sensitivity to our mounting location. I'm not worried about things like nozzles, and I can handle low decay materials. The CLEF algorithm is constrained leading edge fit, where if I have a tank that has a liquid in it, and I get near the bottom of the tank, I can see I can maintain my material surface level instead of getting the bottom of the tank. So because the radar can go through and we're actually measuring the bounce back, when I get near the bottom of the tank, I can actually get it where the signal off the bottom of the tank is actually stronger than the material signal, and I can adjust for that. So we have higher availability. What becomes important is how short my measurement range is, or my blanking distance. When it comes to ultrasonics, the blanking distance is a minimum of a foot because I'm dealing with the speed of sound, and the unit itself rings and has to actually come back to rest. And that resting state of time forces there to be a greater blanking range. With radar, that blanking range is much smaller. The general rule is twice the flange diameter. Okay, so when it comes to a process tank, if I have a 2-inch process connection, then the minimum blanking distance or near distance would be 4 inches. So there are some considerations when it comes to that. Most of the time we're dealing with process connections on a tank, I'll have a nozzle and there'll be some nozzle height, and we want that nozzle height diameter, the height to be no more than 2 times the diameter. So again, a little bit of design considerations there. So again, the flange encapsulated antenna allows us to do both corrosive and aggressive applications at higher temperatures in a number of industries. Since it's fully encapsulated, the process only sees the face here. Okay, so this would be a flanged application. We take a look at the tri-clamp style here. Again, the 2-inch size, 3-inch and 4-inch. Here's a close-up. As you can see, the process connection, this happens to be a 2-inch tri-clamp style. The process only sees the lens, okay? That lens is also replaceable, okay? And so it's a gap-free system. We do meet ISO requirements for that. But we do have replaceable wetted parts. So if that part does get damaged, the whole unit does not have to be replaced. That lens itself can be replaced. We talk about aseptic and hygienic slotted styles. Hygienic slotted nut and the Tugendhagen style. All these are designed from the process of getting all the approvals, both for Europe and for the States. All right. Any questions so far?
We have not had any questions so far, Tim.
Very good. All right, that means everybody's understanding everything perfectly. Okay. A few other considerations when we talk about tanks is we can do these with stilling wells. For applications with solids, we can get into very low dielectrics. Again, the fully encapsulated, what I just talked about a little bit in terms of the nozzles and diameters. In the older style units, we could not be within the nozzle. So we had the LR250 styles, the non-hygienic styles. We had some limitations there that I was actually right into the process. Now, in effect, that horn is outside of the process in here, and the process itself is only seeing the lens. So major improvement in terms of what the materials of construction. If I have an aggressive application, I don't have to go with an exotic alloy that's very expensive. I can stick with a Teflon unit here and be isolated from the process. We talk about some of the applications that we get into, both in pharma, chemical treatments, demineralization processes, cosmetics, food and beverage, quite a few different applications. All of our materials are to 3A specifications. So we get involved in dairy, brewery, soft drinks, sugar, you name it. Large in the chemical industry. Our top customers are basically involved in the food industry. And this has been, the LR250 has been very well received in the industries. Some applications in breweries. When it comes to applications, we actually do have a full applications group. One of my jobs is, as an applications engineer, is to review applications and make recommendations. And we have the tools to do that. We talked about earlier using applications. We'll use radar as a continuous level measurement, and then a level switch as and a process connection as a good engineering practice for fail-safe control, especially in critical processes. We want to have a high-level switch. In this case, this is an extremely nasty application, and they're actually using a point-level switch as an interstice measurement within a double tank wall. So if there was a leak in that wall, this was going to measure that. So when it comes to these applications, we get involved in a lot of hygienic products. Today we're talking radar, but we also get involved, we do conductivity, as I just showed, as well as sanitary style pressure as well. So generally, if we're measuring level applications, just keep in mind that we also handle point level as well as pressure and temperature applications as well. For applications where you're just simply trying to maintain isolation from a chemical, the PVDF antenna style works well. So keep that in mind. You don't necessarily have to go to a hygienic process if you're to use the Teflon. We do have a unit that's PVDF, that's a 2-inch NPT style. And to give you an idea of our portfolio, today we're talking about a very small segment of a whole large range of equipment that we actually provide. So this is the world I generally live in, is level measurement, but we do get involved in flow, everything from irrigation, and then a good portion of what I do also is in regard to weighing. So if we have some applications, we get involved where we just measure from the outside of the tank because the application itself is too we may have agitation or foam and things that may have issues where if we know up front from a design consideration, we could actually do level measurement based on weight. So we can get away from having to put anything into the process itself whatsoever. For these applications, we do use a application data sheet. Let me just mention that real quickly here. So if we were talking, what I would probably do would be send you an application data sheet. This is also available online. Basically, having the best information available helps us help you with making a suggestion in regard to what equipment would work best for your application. So don't be surprised if we're talking and have an application. I'm not jumping to a model number. What I want to do is determine what's the best equipment for the application. So we have guys who are dedicated to doing applications, both in Springhouse, Pennsylvania, down in Arlington, Texas, and also Peterborough, Ontario, where we have some experience with what's worked well in the past. So feel free to talk to your local Lesman salesman on applications, and we'll be able to take a look at these directly and make a recommendation based on that. So given that, questions, comments, concerns?
We have a question. Can we go back to your illustration of use of a stilling well?
Sure.
And then the question is, if you're going to use a stilling well, what's the minimum stilling well size to get a good reading?
Okay. We want to match the size of the general rule is you match the size of the flange with the size of your stilling well so that your stilling well acts as a wave guide. Okay. So if, in this case with the Hygienic 2-inch, I would want to use a 2-inch stilling well. But when it comes to the stilling well applications, we basically want to use the largest size available. So they don't recommend using the 2-inch size with stilling wells, but match the stilling well diameter with the flange size. Let's take a look here.
Tim, that was the only question I had.
Well, fantastic! Wow. If you want, we can go into a little bit more depth on a number of things, including the algorithms. We can also take a look at some of the differences between beam angles, frequency, and why we have advantages to going with higher frequencies, and then matching the frequency to the application, or anything that's more application specific in the industry. If we have questions along that line.
I think if there are those questions, we might want to leave those up to getting them answered on their specific application.
Okay.
Because it would really apply more to that than to a generic situation.
Gotcha.
At this point, Tim, I want to thank you very much for your presentation. If any of the customers do have specific application questions, feel free to give us a call at 800-9-LESMAN or 800-953-7626. If you don't know your account manager, feel free to just ask for me, Mike DeLucluse, and I'll make sure that you get taken care of. I think you also have my email address, so feel free to email me as well. Our next webinar is going to be on February 26th at 9 a.m., and we'll continue on the topic of hygienic inventory measurement basics for liquids and solids inventory management. This time it's going to be presented by Sartorius Intech, and they have a very unique hygienic solution for weighing. You can either sign up through our training center at lesman.com or wait for the email announcement that will be coming out shortly. I still don't have any further questions, so at this point we will conclude the presentation. Again, Tim, thank you very much.
Thank you for your time.